Okay, first of all, I've got a chat box here. Does anybody have a question? Let me, in case some of you missed the 468 section yesterday, let me just show you very briefly how MATLAB solves differential equations. It turns out it's quite nice, at least for simple differential equations. So here's a first order nonlinear ordinary differential equation. And what you do is you first have to tell MATLAB what your symbolic variables are. And these are the function you want to find together with any constants that you are going to use, constants that are abstract as opposed to actual numbers. And so then you say the ODE equals, and in this case, I chose the logistic equation. Diff y is ay over 1 minus y over big Y. I added a condition y of 0 equals y0. And then I say y sol of t is d solve of ODE and the condition. And then I say y sol is simplify y sol so that it simplifies the expression. And indeed, what we get is the solution we had for the logistic equation. For the Legendre polynomials, which I'm going to be talking about later today, what you do is you say sims u of x, x, a condition u of 1 equals 1. That's true for all the Legendre polynomials. This is Legendre's equation. I didn't put it in, well, this is self-adjoint form, but it's not in the simplest self-adjoint form, in which case, you have some parentheses here. I couldn't get MATLAB to recognize what I meant for its self-adjoint form, so I just wrote it this way. Anyway, this is a lot simpler for humans as well as for MATLAB. And then you just say u solve of x, u solution of x is d solve, ODE cond. The semicolon prevents MATLAB from restating what you've stated. And if you don't use the semicolon, then every time you hit return, MATLAB just says what it thinks you meant to say. So then I say u sol of x is d solve ODE condition, and u sol is simplify u sol, and there comes the second Legendre polynomial. That's because I chose LL plus 1 equal to 6, which is for L equals 2. So that's how these things work. Of course, as with anything in today's world, if you don't know the answer to something, you Google it, and then Google will refer you to MathWorks, and MathWorks will, in the best of cases, answer your question. Okay, well, we've been through the early sections of this chapter on integral equations. The basic thing about integral equations is that they rewrite the differential equation in a form that's more suitable to mathematical analysis. And in particular, for linear differential equations, they re-express the differential equation in a form that is suitable for the techniques of linear algebra. And of course, as I've mentioned to you, and as you know from using MATLAB, computers can now basically solve all linear algebra problems in microseconds. That's a slight exaggeration, but in most cases, that's exactly right. I remember when I was a graduate student, having a computer solve a 50 by 50 matrix equation was a big deal. And it used, you need a big deal on the latest IBM 7090 computer. Nowadays, you can have MATLAB do it for you in microseconds or fractions of a microsecond. Anyway, so these things all get re-expressed as linear equations. And one aspect of linearity is that if you have various eigenfunctions with the same eigenvalue, then any linear combination of them is also an eigenfunction with the same eigenvalue. And if you have an inhomogeneous equation with a given eigenvalue, then the difference of any two solutions of the inhomogeneous equation, of course, when you take the difference, the inhomogeneous term cancels. And so the difference of any two solutions of the inhomogeneous equation, in other words, this thing, is a solution of the homogeneous equation. So you write the general solution of the inhomogeneous equation as any particular solution of the inhomogeneous equation, I being inhomogeneous, plus the general solution of the homogeneous equation. And as I said, you can turn these problems, if they're linear, into linear algebra problems, in which case you take, for example, this homogeneous Fredholm equation of the second kind. Well, it's an eigenvalue equation. You split the interval from A to B into n intervals, n subintervals with n+1 endpoints, and you then have an algebraic equation defining capital K sub KL as the kernel of x, k, y, l times the length of the interval, and the unknown eigenvector as, or eigenfunction, you turn it into an eigenvector by this discretization, and you have that u sub k is u of yk. So you then get this linear equation, and and that leads to this determinant equation, which gives you the eigenvalues in as I said, microseconds. You can apply the same technique to an inhomogeneous Fredholm equation, and you then get a matrix equation that looks like this. The homogeneous equation, Ku is lambda u, has n+1 eigenvalues and eigenvectors. And if you pick a lambda that's not one of the eigenvalues, then this thing has a non-zero determinant, therefore an inverse, and you can solve the inhomogeneous equation this way. You just say the inhomogeneous solution is k minus lambda I inverse on F. I think I'm going to skip the rest of this section. It's a little bit technical. Those of you interested, I think, can read it on your own. If somebody becomes interested in this and wants more detail, send me an email and we can talk about it in detail on Wednesday in the 468 class, or if you have a specific question on this, send me your question and I'll try to answer it by email. Now, integral transformations are something that's somewhat magical, actually. So suppose you have a linear homogeneous differential equation that looks like this. Of course, once it's linear, you understand that basically we should be able to solve it. It's the nonlinear problems that are really hard. Anyway, suppose it is a linear differential equation and homogeneous in this case with an eigenvalue here, lambda squared, plus or minus lambda squared is playing the role of an eigenvalue. And so the trick here is that you choose a kernel K of two complex variables, Z and W, and then you write the solution as an integral of this kernel that you choose times some V of W that you're also going to choose, and you require that it solve this thing. And so if it's to solve that thing, then if for example, we're saying that, well, what is the equation? The equation, let's see, I think I left out a key equation here. Well, maybe not. All right, so what we're saying here is that U is the integral of KV. And so our equation is LU, and if L hits this, it can go inside because it's just acting on the Z's. So L acting on the Z's minus lambda squared K VW is 0. So that's what we have. Now, the next thing is that one must find a linear operator M acting on K that gives us L acting on K. Now, M is something that only involves W derivatives. And you might say this is nuts, but as well, once again, Roy Glauber once said to me, often in physics and mathematics, you make progress forward by going back a few steps. And so you do this thing that's kind of weird. You say this differential operator acting on W hitting K is the same as L, which is a Z differential operator acting on K. Then you have this equation, which involves only W derivatives now. And you can integrate that by parts. Then you choose the contour so the boundary terms vanish. And then by using the freedom to pick the kernel and the contour, the differential equation for V, and therefore the answer for U, are these differential equations are simpler than the ones we started with. And you might say, gee, I've never seen this. Well, you have seen this because here's a Fourier transform. So that's expressing the unknown function in terms of a kernel of Z and W, and then a W. Now, normally when we think of a Fourier transform, Z is real and W is real, and that's an ordinary Fourier transform. Another possibility is the kernel is e to the minus ZW, and then when Z and W are real and W is only integrated from 0 to infinity, this is a Laplace transform. But in general, it's more general. In general, it's more general. Well, anyway. Euler's kernel is Z minus W raised to some power, and it occurs in the Cauchy integral formula and the Cauchy integral theorem. And in particular, I think I'm going to postpone this example until we get to the chapter on Bessel functions, where it's more relevant. Anyway, what happens is you can express the most general Bessel functions then as integrals in the complex plane, and these are integrals that run basically up an imaginary axis. Okay, well, we're moving very fast. There is plenty of time for questions. Does somebody want to ask a question? Either using the chat box or speaking up. But again, I'm hard of hearing, and sound over Zoom isn't all that great. So if you speak slowly with an American accent, I have no trouble, but otherwise, sometimes I do have trouble. I've got hearing aids, but they are not 100% by any means. All right, let me go on with Legendre polynomials. The monomials x to the n span the space of functions that have power series expansions on an interval about the origin. And of course, this is just the Taylor series expansion of a function about the origin. And these monomials are complete, but they're not orthogonal and they're not normalized. And what Legendre did was to make them orthogonal and make them and to normalize them and also give make them unique by adding yet another condition. And so what he said was the polynomial p sub n. Now, why it's p sub n and not L sub n, in as much as it's Legendre who invented them, that I don't know. Of course, P is the first letter of polynomial, but I would think we ought to call them the L sub n, but I think most people do call them P sub n. Anyway, he picked the interval -1 to 1 and said, okay, we're going to require that that these polynomials are orthogonal in that when n first of all is an integer and m is an integer. For integer values of n and m, if the integers are different, we're going to get 0. So that was the first requirement, that they're orthogonal. And the way he chose them to be orthogonal was rather cute. What he said was that the polynomial p sub n is going to be orthogonal to all monomials x to the mth for m less than n. So in other words, if this is p2, then it's orthogonal to x and to the number 1. If this is p6, then it's orthogonal to x to the 5th, x to the 4th, x to the 3rd, x squared, x, and the number 1 or 2, whatever. Anyway, this is the condition. And now, since this is an nth order polynomial, it actually has n+1 coefficients, these guys plus that one. And so we added one more condition, which is that the Legendre polynomial at 1, which is the right-hand end of the interval, equal 1. Then they're unique and they're called the Legendre polynomials. And I made a figure out of them, and that's what's on the book cover. So the coefficients, here's, for example, the first 20 Legendre polynomials, what they look like. And it is a pretty remarkable thing. I mean, one can stare at this for quite a while, and it's kind of interesting to look at. Anyway, this is P0 is just the number 1. P1 is just x. And then P2 is 3x squared minus 1 over 2. That's the thing that we got as a solution using of Legendre's equation using for L equals 2 using MATLAB. Anyway, so the conditions of orthonormality are, if you write Pn like this, then you get these conditions, which are n conditions, and then you have one more condition that the sum of all the a's be unity. And you can use those conditions to build the things up P0 is 1, P1 is X, P2 I just mentioned. What's P3? P3 is 5x cubed minus 3x over 2. P4 is 35x to the 4th minus 30x squared plus 3 over 8. Anyway, Rodrigues, I wish I had studied Spanish and knew how to enough to know how to pronounce that guy's name. But anyway, he developed a very nice formula for the Legendre polynomials, a normalization factor, then the nth derivative of a polynomial of degree 2n. And this polynomial has the nice feature that it can be factorized in this way. And you then get a formula for Pn of x, and it's just this sum of these combinatorial factors times these monomials there. And if you set x equal to 1, then these guys all vanish, and you're left with just the case where k is equal to n, and that gives you the binomial coefficient nn squared, which is 1, and then you have 1 over 2 to the n, and then you have here, this is 2 raised to the power n, so you get 1. So Rodrigues got the normalization right, and you can then use Rodrigues's formulas to compute these things. And one way to do that, of course, is to use the Leibniz formula, something that we looked at in chapter on infinite series. In MATLAB, mfun pnx returns the value of pn of x. You notice the capital P here, apparently it's just universal, but instead of L for Legendre polynomials, we're using P. I guess somebody must know the answer to why that's true. I don't know. Maybe it's that Legendre was a very avoided bragging and didn't want to use L sub n, and everybody copied his use of P sub n. Maybe that's it. I don't know. Anyway, to check that these are orthogonal, we want to see whether this vanishes when m is less than n. And if you use Rodrigues's formula, you see it's the nth derivative of this thing. You integrate by parts n terms, and then you get the nth derivative of x to the m. You drop all the surface terms because this monomial vanishes at the two endpoints, -1 and +1. And then obviously if m is less than n, this derivative vanishes. And so Rodrigues's formulas gets the orthogonality as well as the normalization right. And one can then show that the Legendre polynomials satisfy this particular normalization condition. Let me go back to the very beginning here to say what it is that Legendre said. Well, he said the Legendre polynomials, what's of degree n, obviously P sub n, that it's orthogonal on this interval to the xm for m less than n, and it's normalized. These are n+1 conditions on n+1 coefficients, so that uniquely determines them. So in other words, what determines the Legendre polynomials is these two equations, 9.3 and 9.4. So I just want to emphasize that. So let's see, I think that's where we were. So generating function for Legendre polynomials. Now, I have always found generating functions to be magical. There are a lot of magical things in mathematics. when I was an undergraduate, I almost went into mathematics as a graduate student instead of physics. I finally chose physics because I didn't understand what mathematics was. So I thought, well, if I don't really know what it is, maybe I shouldn't go into it as a field. I think I might have been more at home there. Anyway, this generating function is g of t and x, and it's this little polynomial here, raised to the power minus 1/2. This is the generating function for the Legendre polynomials. And as I said, I find this to be a magical formula. All of these generating functions strike me as being absolutely magical. Anyway, the coefficient p sub n obviously is the nth partial derivative of g of t and x, evaluated at t equals 0. Because this is a Taylor series of this function about the origin on the t line. And this is just a function of x. And one can show that it's actually a polynomial of degree n. To see what they are, we can use the logarithmic series. Let me just see if I can flash that. There's the logarithmic series, log of 1 plus x over 1 minus x. So first we integrate g of tx, g of vx, dx, and we have this integral. Now it turns out that that integral is this log. And if you then use the logarithmic series, what you get is this as the series. On the other hand, what do we know about this? Well, this is a sum of Pn t to the n. And so this is some Pn t to the n, some Pm v to the m. And now we want to equate coefficients of t to the m, t to the n, v to the m. And what we see is we get this orthogonality relation. And indeed, this tells us that the little p's satisfy the orthogonality relation that Legendre used to define his polynomials. And then to see that they're normalized, namely that little pn of 1 is equal to 1, what we do is we go back here and we set x equal to 1. And then this is 1 minus 2t plus t squared. That's 1 minus t squared to the minus 1/2. So that's 1 over 1 minus t. And then on the right-hand side, that's p to the pn of 1, t to the n. On the other hand, 1 over 1 minus t, you know, is the sum of t to the n, at least for small t. And so picking off the coefficients, we see Pn of 1, it has to be equal 1. So these Pn's are the Legendre polynomials, and g of t and x is their generating function. And this particular expression here occurs in the Green's function, the Coulomb-Green's function, 1 over r, or 1 over r minus big R minus little r. And it satisfies this minus Laplacian on g is the delta function. And if we set x equal to cosine theta, which is the dot product of the r's divided by their lengths, and t equal to r over r, and factor out a 1 over r, we can write this as 1 over big R times g of t and x. And now we know that that is just a sum t to the n pn cosine theta, pn of x being cosine theta, t being r over r. And so this is a famous formula for the Coulomb-Green's function expressed in terms of the Legendre polynomials. Let me just make a note to myself. Okay. Okay, Legendre's differential equation. Well, it turns out it's we can, with these generating functions and sometimes with other tricks, we can uniquely define various special functions or orthogonal polynomials, but finding the differential equation they satisfy is sometimes more difficult. In this particular case, what one does is set u equal to x squared minus 1 to the nth power. That basically is what goes into Rodrigues's formula. Then we can see that u prime is given by this. We multiply by x squared minus 1 and we get this expression. And then we use Leibniz's rule, which you remember is how to differentiate the product of two functions. And we differentiate both sides of this equation. Well, we get this expression here, and we also get this expression equating the two. We get finally Legendre's equation in self-adjoint form. This differential operator, just to remind ourselves, it's formally self-adjoint. The real function p is positive on the open interval, vanishes at the endpoints. So Legendre's differential operator, his differential equation, the domain D of functions that are twice differentiable on the interval, form a singular self-adjoint system. Singular because p vanishes at the endpoints. The Legendre polynomial is an eigenfunction of L with eigenvalue nn plus 1, weight function w of x equal to 1, the orthogonality relation, that's this orthogonality relation, tells us that eigenfunctions of a self-adjoint differential operator that have different eigenvalues are orthogonal with respect to the weight function. Well, that's what we derived earlier, which follows from the Rodrigues formula. The eigenvalues are nn plus 1, and as n goes to infinity, they go to infinity. And that shows that the Legendre polynomials are complete. And just to illustrate that, now let me see exactly what. All right, I guess that's the entire description. In here, what we've got is the sum of the first 10,001 terms in this expansion. So in other words, this thing is supposed to give us the delta function. And in fact, you see that here, the x-axis here goes from minus 0.1 to plus 0.1. The y-axis goes from minus 500. In other words, this y-axis spans 4,000 units, and this spans 2/10 of 1 unit. So this is an amazingly high spike, and this is a very small distance compared to the y-axis. And so this, in the limit, this really is the delta function. And these coefficients here are, let's see, that's a section rather than a, okay, so these, what I'm a little puzzled about is what exactly that came from. So let me just write a note to myself to explain why we have exactly that. All right, I'm going to have to think about that. Anyway, we multiply both sides by any twice differentiable function. And what we get here is this is equal to the delta function integrated delta function of x minus x prime f of x prime dx prime is automatically f of x. And using this expression, we have the PNs come out, and then we integrate like that. And if we now switch to variables to cosine theta equals x and sine theta is 1 minus x squared, we have these relations and this relation. And Legendre's equation then takes this form, which is the form that it often occurs in physics problems, because we often use Legendre polynomials when we're dealing with problems in spherical coordinates. The generating function gives us a bunch of recursion relations. If you take the t derivative, you get that. You can then rewrite it in this way, and if you equate coefficients of t to the n, you get this expression, which is called a recurrence relation. And that allows you to build up the Legendre polynomials. In fact, computer programs very often use recurrence relations rather than something like Rodrigues's formula. The x derivative of the generating function looks like this. You rewrite it that way, equate powers of t to the n, and you get another recurrence relation. And now you can then get a dozen more recurrence relations. Eventually you recover Legendre's equation. If we set x equal to -1, we get this expression, 1 over 1 plus t. That's the sum of minus t to the n. That's got to be the sum of Pn of -1 times t to the n, because x is -1. And then comparing these two, we see Pn of -1 is -1 to the n. So now we know the values of every Legendre polynomial at 1 and at -1. Let me just jump over here and go back to here. And we see here, therefore, at -1, we have all the even Legendre polynomials get the value 1, the odd ones get the value -1, whereas at x equal to +1, all of the Legendre polynomials jump up to the value Pn of x equal to Pn of 1 equal to 1. Okay, so let's see, where was I? Special values. The generating function's even under reflection, and that tells us that Pn of -x is -1 to the n Pn of x. And in particular, that tells us that Pn plus 1 of 0 vanishes. And I guess maybe it's worthwhile looking at that again. So you see here that the odd Legendre polynomials vanish at x equals 0. That's why there are half of them, 10 of them in this particular case, 10 or 11 actually, go through the value 0 here, the origin in this plane. Jumping back to this equation, so let's see, where was I? Right. This is actually very important in physics, because the wave functions of many atomic and nuclear systems involve the Legendre polynomials. And when you flip x to -x, you get -1 to the n, and that leads to various conservation laws. especially in atomic physics, which of course is better understood than nuclear physics, but also in nuclear physics. At least I assume so. I don't know that much nuclear physics. Anyway, with more effort, one can show that the even ones are given by this at 0, and so some of them are positive, some of them are negative. Notice one thing, though, that these Legendre polynomials, at least these formulas for the Legendre polynomials, involve big n factorials. In other words, if n is, say, 20, then you've got things like 20 factorial occurring, or in this case, double factorial. And these are these are numbers. These numbers get so big that computers have trouble handling them. I mean, in double precision, I think you can go up to 10 to the 308 or something like that. And of course, you can go to quadruple precision, and then you go even higher. But at some point, n factorial just beats everything. And the NIST webpage, and by the way, the NIST, National Institute of, I guess, Science and Technology, they have web pages that contain a lot of mathematics and engineering and physical information. They're one of the places, one of the go-to places. Another go-to place is the particle data group. Let me get rid of that and just write down what that is. So particle data group. That's at Berkeley, and they have all kinds of information about particle physics, and NIST has a great deal of information about engineering, science, and mathematics, especially mathematics, applied mathematics. Anyway, they give an approximation involving the arc cosine and the 0th Bessel function. And so I don't know, I applied it to this case, and I'm not quite sure what use this formula 9.54 is, but there it is. Anyway, there's a second solution, of course, to Legendre's equation. And instead of the polynomial, we get something called Qn. And the Qn's are Legendre polynomials times log terms, and then a W. And the W is itself a polynomial in Legendre polynomials. Okay, well, that's probably not the most important thing in the world for us right now. There's a Schlaefli, or Schlaefli, anyway, used Cauchy's integral formula and Rodrigues' formula to express Pn as a counterclockwise contour integral around the point X. So this is an integral around the point X. And of course, what does it tell us? That says that this integral is then the nth derivative evaluated at z equal to x, and times divided by n factorial, and so it just gives us back 958. Now, Legendre polynomials are orthogonal polynomials, and there's a whole family of orthogonal polynomials, or I should say there's a whole generation of families of orthogonal polynomials. And you can generate them using a generalization of Rodrigues's formula. And in fact, I'm sure Rodrigues himself introduced this formula. And the nth order polynomials, you have normalization constants. You pick a particular weight function W of X and a particular function Q of X. You raise Q to the nth power, differentiate n times, and then you automatically get that they're orthogonal or orthonormal on the interval as long as Q vanishes at the endpoints of the interval. And examples of this are, you let Q of X equal to X squared minus 1. Well, that's what we had in the case of the Legendre polynomials. But here, instead of differentiating simply Q to the n, you pull in a weight function W. And for the Jacobi polynomials, it's 1 minus x to the alpha, 1 plus x to the beta. And you normalize them with En equal 2 to the n over n factorial, which in fact is the Rodrigues normalization of the Legendre polynomials. And then what you find is that as long as alpha and beta greater than -1, you get these Jacobi polynomials, and they then, from this recipe, are just given by this. They turn out to be orthogonal on -1, 1. They have, the integral is this. They have this normalization condition. This is the differential equation they satisfy, and there's a generating function that generates them in terms of an R that's very much like the generating function of the Legendre polynomials. If you set alpha equal to beta, they're the Gegenbauer polynomials. And if you set alpha and beta equal to plus or minus a half, they're the Chebyshev polynomials of the first and second kind. And if you set alpha and beta equal to 0, you get back to Legendre polynomials. So on the left are the Chebyshev polynomials of the first and second kind. Okay. What's really one set of polynomials that is important in physics is the Hermite polynomials. And here you set Q of X equal to 1, weight function e to the minus x squared, and you then have Hn of X is equal to this, and you can rewrite that as this. And if you let big D equal to d by dx, it's 2 to the n e to the minus d squared over 4 on x to the n. Let me do another note to myself. These are orthogonal on the real line. They satisfy this differential equation and have, again, a magic generating function. And the nth excited state of the harmonic oscillator, mass m, angular frequency omega, is proportional to this, in which x is related to q by this factor here. And x is the dimensionless position of the oscillator. And I see here I've screwed up the indexing of things, or the reference here. Well, all right, I've got to fix that. Okay, Legendre polynomials, and these occur in the hydrogen atom, the non-relativistic hydrogen atom. You set Q of X equal to X, weight function like this, and these are the generalized Legendre polynomials. They're orthogonal on 0 to infinity. And why is it 0 to infinity? Well, because they're used for the radial function of the hydrogen atom. And they're orthogonal on this interval. they satisfy this differential equation, which somehow staggers out of Schrodinger's equation. The generating function is now, you know, how did anybody figure this out? I don't know. And as I said, the radial function of the non-relativistic hydrogen atom is rho to the L, L, 2L, up at 2L plus 1, lower n minus L minus 1 of rho, e to the minus rho over 2, and rho is 2R over n A0 being the Bohr radius, which is about a Fermi, not a Fermi, about an angstrom, half an angstrom, I think. Okay, so azimuthally symmetric Laplacians. Well, Laplacian separates in spherical coordinates a system that has no dependence on phi is said to have azimuthal symmetry. And an azimuthally symmetric function then looks like this. And it's going to be a solution of Helmholtz's equation if R and theta satisfy these two equations. And the theta equation is Legendre's equation that we saw before. So we can set big theta equal to the Elf Legendre polynomial of cosine theta. If K is positive, the solutions of this radial equation that are finite at the origin are spherical Bessel functions. Spherical Bessel functions are quite nice functions, especially compared to cylindrical Bessel functions. You see, the sphere has such symmetry that the solutions associated with it are simple, whereas the cylinder has less symmetry. It only has azimuthal symmetry, and consequently, the cylindrical Bessel functions are rather complicated infinite series and not related to much that to other functions that I know of. Now these spherical Bessel functions are given by Rayleigh's formula, and they're just simple derivatives and powers of sine x over x. So that's really a very, very nice formula, especially if you've seen formulas for the cylindrical Bessel functions. And so the general azimuthally symmetrical solution of the Helmholtz equation, finite at r equals 0, is this expression here. If the solution can be infinite at the origin, then there are spherical Bessel functions of the second kind called Neumann functions, which are also nice functions. They must be included, and then we have something like that. If k equals 0, you just have Laplace's equation, and then that looks like this. And if you set r sub L equal to r to the n, you then see that n plus 1, differentiating, n plus 1 is equal to LL plus 1. So n has to be L or minus L plus 1. And so the general solution looks like this. This is, again, the electrostatic Coulomb potential. And if it needs to be finite at the origin, all the B's vanish. This is something that you've probably seen several times in courses on electrodynamics, and in particular electrostatics. So if we go down to 2 dimensions, Helmholtz's equation in cylindrical coordinates separates, and if k equals 0, it reduces to Laplace's equation. If it's independent of z, even simpler solutions exist. And at this point, one has alpha equal to k equal to 0. I must say, just looking at this, what is alpha? I think I should say what alpha is here. In any event, one sets phi double prime equal to minus m squared phi squared, and then this equation here. So let me, well, this is not showing up very clearly. All right, let's go back to, so this is the Helmholtz equation in cylindrical coordinates. And now if I can get back to where it is that we were, I think we're here. Yes, that's where we were. Then the equation for P looks like this. And phi, of course, we can set as e to the im phi. If the whole range of phi is physically relevant, then phi has to be periodic. On the other hand, if as I've said this to you before, but if the only part of phi that's physical is here, then phi need not be periodic, because we'd have to go around an unphysical region to get back and to see some kind of ambiguity here. And to solve this equation, let me see if I can pull this down. Right. For P, we set P equal to rho to the n, and we get this expression and consequently that. I think this was bad notation here. I shouldn't use P to the m. So because we just decided that this was the Legendre polynomial, and so this is completely misleading. This was actually a capital rho. That's the way I was thinking of it, rather than a P. Anyway, what we get is n is equal to plus or minus m, and so we get this expression in cylindrical coordinates. So let's see, I don't see anything in the chat box as a question. So in spherical coordinates, we've seen Laplacian separates, and we get these expressions. And this is what we use most often, because we most often have actual spherical symmetry. And this is a solution of Helmholtz's equation. If R is a linear combination of spherical Bessel functions, phi is e to the im phi, and theta satisfies the associated Legendre equation. This again is something you've seen in electrodynamics classes. And this associated Legendre polynomial is a particular multiple of something called the associated Legendre polynomial. And this associated Legendre polynomial is a polynomial in sine theta and cosine theta, or effectively a polynomial in x and square root of 1 minus x squared. This complicated square root is just to have nice normalization. So let's look at these associated Legendre polynomials. They arise as solutions of the separated theta equation. So we have this expression here. Once again, I'm using P for everything, and I think I shouldn't do that. Well, I don't know. Anyway, this is then part of the Laplacian, the theta part of the Laplacian in spherical coordinates. If we set x equal to cosine theta, then this becomes a self-adjoint ordinary differential equation. And this is the Legendre differential operator. The LL plus 1 times P is the Legendre part, and then the associated polynomials involve this m over root over square over 1 minus x squared. And it turns out that this associated Legendre polynomial is simply related to the mth derivative of the Legendre polynomial. So I guess it's okay to use P here. And now that I think about it, earlier, you notice that the P was standing straight up, whereas these P's are in italics. The reason it was standing straight up is that the Greek letters in LaTeX are all, at least the capital Greek letters, stand up straight vertically. And that capital P was actually a capital Greek rho. And so that's how I was thinking of it. Anyway, this is simply related to a derivative of the Elf Legendre polynomial. And now what we want to do is we want to see that this does satisfy this differential equation. And so we differentiate this quantity here. And so PLM of X is this is how we defined it. No, wait a second. The mth derivative of PL of X is so. All right, let me just try to get this straight again. This thing here we're defining this way, and so this part is 1 minus x squared to the minus m over 2 times this. So this implies that. We differentiate it twice. We first get this expression and then that expression. Then we use Leibniz's rule to differentiate Legendre's equation, this equation, m times, and we get this expression. Now we put the formulas for the three derivatives, this one, and that one, into this equation, and we find that PLM does obey 9.98, which is this equation. So we verify that this satisfies that. So the associated Legendre functions then are derivatives of the Legendre polynomials, mth derivative of the derivatives of the Legendre polynomials. Of course, parenthesis m parenthesis means mth derivative is in a certain notation, multiplied by 1 minus x squared to the m over 2. And in angular terms, it's sine theta to the m, and then the mth derivative with respect to cosine theta of PL of cosine theta. And one can use Rodrigues' formula for Legendre polynomial to write this as that, because PL is already 1 over 2 to the L factorial, the mth derivative of P of x squared minus 1 to the L. And now that we've got this expression here, we can extend it to negative values of m. M, remember, was the number of times you differentiate. But in this expression, we can have m negative as long as it doesn't exceed L. And so then, and then also we find that if we flip x to minus x on PLM, remember we got that this, for m equals 0, we had minus 1 to the L. Now for m not equal to 0, it's minus 1 to the L plus m. So this is the thing that leads to the to some of the selection rules. In fact, many of the selection rules of atomic physics. Condon and Shortley have an extra phase. I don't know if we need to know that. So as I said, Rodrigues' formula makes sense as long as L plus M is non-negative. And this is, in quantum mechanics, the requirement that M not be less than minus L. And also, if M is greater than L, then PLM is given by more than 2L derivatives of a polynomial of degree 2L, so it vanishes. And so this leads to what you see in quantum mechanics, namely that M has to be between minus L and plus L. Of course, there are other ways to derive that, but it's another way of thinking about it physically is this is the angular momentum in the Z direction, and it can't be bigger than the angular momentum, the total angular momentum, which is L, more or less. Anyway, since M occurs only as M squared in this ordinary differential equation, PL minus M must be proportional to PLM. And in fact, the proportionality is given by this expression here. If M is not equal to 0, then PLM has a power of root 1 minus x squared in it. So PLM at plus or minus 1 vanishes. And this is something that has many important implications in scattering theory and the shape of atomic wave functions and nuclear wave functions and so forth. Now, the ordinary differential equation satisfied by the associated Legendre polynomials is this expression here. And you can focus on this one as the eigenvalue, or as this one as the eigenvalue. If LL plus 1 is the eigenvalue, the weight function is unity, and this thing is part of the differential operator. And this ODE then is self-adjoint on minus 1 to 1, and at the ends of which P of x vanishes. The eigenfunctions must be orthogonal on that interval when L is not equal to L prime. So for fixed M, PL prime M is proportional to delta LL prime, and this is the factor. If on the other hand, you take M squared for fixed L as the eigenvalue, then the weight function is 1 over 1 minus x squared. The eigenfunctions must be orthogonal when M is not equal to M prime, both having the same value of L. So PLM prime, and now we divide by 1 minus x squared. They're proportional to delta M prime. So let's see, I'm rattling along here at high speed. I guess one advantage of that is that I'll be able to squeeze more general relativity into the course, which is, I think, a good thing. Okay, the spherical harmonics are the product of the associated Legendre polynomial and this phi m of phi, and this is just e to the im phi. So this big theta is equal to the associated Legendre polynomial of cosine theta times this normalization factor, and phi m is a normalization factor e to the im phi, and so these are called the spherical harmonics. The eigenvalue equation and that of phi m, which is this, imply that the spherical harmonic satisfies this equation, and the big square root ensures that the y's are normalized, completely normalized, delta LL prime, delta MM prime, when integrated over the unit sphere. So that's all phi from 0 to 2 pi and theta from 0 to pi. And in spherical coordinates, the parity transformation, in other words, reflection of the 3-vector x, is r is unchanged, but theta changes by, theta goes to pi minus theta, phi goes to phi plus or minus pi, and so cosine theta prime is minus cosine theta, e to the im phi prime is e to the is minus 1 to the m e to the im phi, And so that's a minus 1 to the m. That cancels the m dependence of this under parity. So under parity, YLM reflection is YLM of pi minus theta phi plus or minus pi. That's minus 1 to the L YLM of theta phi. So the parity of one of these atomic states is minus 1 to the L. And as I said, this is what occurs in atomic and nuclear physics. The spherical harmonics are complete on the unit sphere, and they can be used to expand any smooth function as, well, you just sum over all LMs. L from 0 to infinity, M from minus L to L, and you just sum over all of them. And then we have an orthonormality relation. That was that the spherical harmonics are completely orthogonal, and that allows you to derive this expression here. And the way you derive that, of course, is that you say, if you multiply y star of, let us say, theta phi Lm, f of theta and phi, and you integrate d phi and sine theta d theta, well, f is already a sum. This is equal to an integral y star Lm theta phi. And now this is going to be a sum a L prime M prime y L prime M prime of theta phi. And gosh, and now we integrate this d phi sine theta d theta, and then we use the orthogonality relation of the y's, and this just gives us ALM. And so that's the formula here, that ALM is the integral of y star times f. In other words, that gives us this formula. This is equal to that, which is equation 9.123. And if you put the two together, you then write f is equal to that, and you set the a's equal to this, you then rearranging, you get this expression. And that tells us that the sum over all the Legendre, associated spherical, all the spherical harmonics gives you a delta, an angular delta function. And there's a 1 over sine theta that has to occur. And this is sometimes written in this way. Well, we're just about out of time. So we're ending at equation 9.126. So I'll pick up there on Tuesday. Let me just mention that you should be going to the, or viewing over Zoom, the, in fact, I'd recommend just viewing over Zoom rather than actually physically going to the colloquia. The colloquium given by Turner is one that if you missed, you should look for on YouTube and watch. There's going to be an interesting colloquium tomorrow on the lifetime of the neutron. One of the really embarrassing things about particle physics at the moment, I mean, we spend, billions of dollars on these huge underground accelerators, and yet we've got this particle called the neutron that's inside almost every nucleus, and it decays. Its decay isn't hard to measure. I mean, it's not, 10 to the minus 20 seconds. It's more like 15 minutes. And so you'd think that physicists would have gotten it right, in as much as I think it was Chadwick discovered the neutron back in 1920, somewhere back there. when England was leading, England and Germany were the leaders in physics. And, you know, I mean, 100 years have gone by and we still don't know the lifetime of the neutron. And we've got two different ways of measuring it, beam and bottle measurements, and they differ. And it's a little bit like the Hubble tension between the CMB value of the Hubble constant and the astronomer's value of the Hubble constant. And this is really quite, so anyway, you can watch it over Zoom tomorrow. The password is, let me just make sure you know the password, it's PANDA. Okay, well, look both ways, crossing streets. I take it there's no question, and so I'm going to stop now. Bye.